do that over. Or maybe I'm out of hard drive space. I don't know. So both the Old and New Testament talk about what has been made out of what was not made. So both Big Bang cosmology and if we're going to read any science out of Scripture are agreeing that ex nihilo creation is what happened.
I got a question, another one. If you're at the North Pole and you look out as far as you can see with a telescope, you can see 13 billion, 12 billion years out. I don't know how far they can go, but pretty far. You go to the South Pole and you look in the other direction, the same distance.
Well, it doesn't matter where on Earth you are.
Right.
Yeah.
So those two, well, they are on opposite points. So those 2 points would be more than 20 billion years apart, light years apart.
Yeah, so that's called the Hubble horizon. That's how far light has been able to travel since the universe began. And that defines the observable universe, not the whole universe, but the observable universe. Right. It's the only part of the universe that science can directly probe. We can infer that there's more universe out there, but that light hasn't had time to get here from those parts yet. Right. So you've anticipated my next slide. The speed of light. The speed of light has been measured and is exactly 299,792.458 kilometers per second. And it is exactly, because they redefined the meter to fit this. They measured it, they got pretty close, they're like, all right, we're just going to redefine a meter so that it's this exactly. And so a meter is how far light travels in a vacuum in 1 over this number of seconds. Now, the speed of light, c, is also related to 1 over the square root of what's called the magnetic permeability of free space and the electrical permittivity, permeability and permittivity.
Dielectric. Yeah.
Dielectric constant, yeah. This is one reason we have confidence that the speed of light has been constant for the entire universe. A lot of young Earth creationists like to invoke a much faster speed of light early on to explain why we can see light from galaxies more than 6,000 light years away. They invoke a faster speed of light. The problem with that is that you would then go monkeying with these numbers right here, which would in fact change how electrons orbit atoms, how protons work, because these things are electrical and magnetic entities. An electron, because it has spin, also has a magnetic field associated with it. You'd go monkeying with it, these atoms and molecules and nuclei of atoms would fly apart, and we would just be bathed in radiation. And so the problem with changing this constant, you just change lots of other constants, and then the universe wouldn't work. And I don't see God as being that messy. He's more elegant than that, I think. Andrew.
Didn't they come to realize that light moves at the same speed through air as it does through empty space?
No, not at all. Light is slightly slower through air because the electrical and magnetic permeability and permittivity of air are slightly different than for a vacuum.
I was watching some documentary and it was talking about light and how it travels, and they I forget what they proved about light. I don't know. I thought it was that.
Is the speed of electricity close to the speed of light?
It depends what it's traveling. It depends on the resistance.
Say copper for common thing. I mean,
it's about 7 cents in copper.
Okay.
But a lightning strike or that light that's emitted, it's from low frequencies up to X-rays. It's all.
It's still pretty darn fast.
Yeah.
You cook it.
Yeah, as Drew said. So, if the speed of light is constant, and we can get at the age of the universe based on how far away things are and how long it would take the light to get here. So then we have to ask, well, how can we measure distances in space if we can't send spacecraft there? The furthest we've ever sent a spacecraft is Pioneer 11, launched in 1972-ish, and it's 40 to 50 times the Earth-Sun distance. It's still pretty close in cosmic terms.
It's still operating?
No, it's not.
Oh,
Voyager 1
still
is operating, and it's not far behind Pioneers. And New Horizons is catching up, that we launched in 2004. The first one is, well, and within the solar system, we can use radar. We can just ping, like Mercury, with Arecibo radar and know how far from range to it. So within the solar system, we can use radar. Outside the solar system, we use what's called trigonometric parallax, which is it's high school trigonometry. So the idea behind this is that it takes Earth 6 months to go halfway around the sun, and in that time, it's moved 2 astronomical units. We define the distance from the Earth to the sun as 1 astronomical unit, so in half a year, it's gone 2 astronomical units. By looking at nearby stars, we see them appear to shift positions just because we're looking at it from a different perspective. It's the exact same as holding out your finger here, closing one eye, and then alternately blinking your eyes. It looks like your finger's moving relative to what's further away. And if you know the distance between your eyes, we know the distance here, and you know the angle, just from simple trigonometry, you can get the distance. That's it's like a direct measurement. There's nothing controversial about this whatsoever. This will get you out to 10,000 parsecs, which is 32,000 light years. So that's already way older than young Earth creationists say the universe is. So that's enough. So it used to be, 15 years ago, it would only get you out 100 parsecs, or 326 light years. Now with the new mission called Gaia, which was launched 3 years ago by the European Space Agency, it's really precisely measuring the relative position of stars as Earth goes around the sun. And it's good out to the galactic center of the Milky Way galaxy. Now, if young Earth creationists are right that, and if the speed of light's constant, then we'd only be able to see 6,000 light years out, which is like, here's the sun, it would be like, it's like not even a pixel on the screen. Like, we'd only be able to see that tiny bit around the sun if young Earth creationists were correct about the age of the universe. Now, so that's good out to here, trigonometric parallax. Out here, the stars are too far away that moving this amount of space won't really seem to affect their position. So we have to use other techniques. That technique there, and I'm skipping over some of this, but so parallax will get us out. So this I had to update. The parallax will get us out to here. From here, we have to use a type of variable star called a population 1 Cepheid variable. What all this is saying is that astronomers have discovered a type of star that pulsates. And how fast it pulsates is directly related to how bright it is. And offhand, I don't remember if it's brighter, if it's faster, or dimmer, if it's slower, or whatever. It might be the reverse, I'm not sure. But if it's pulsating a certain speed, we know how bright it really is. But if it looks dimmer than that, then we can figure out how far away it must be to look that bright.
So are these quasars or something else?
These are Cepheid variable stars. These aren't quasars. These are Cepheid variable stars.
But I mean, are they optical versions of quasars? Or
they're not quasars, but
okay.
they're just stars.
Just stars.
That are somewhat unstable that pulsate.
And are any of those within that observation window, less than
Yes.
32,000?
Yeah, they overlap. So this bar has now been extended up to here, and they overlap a good chunk. So if you find Cepheid variable stars that you can also get their distance from trigonometric parallax, then you can calibrate how far away they must be based on their pulsation. From there, we can go up to type 1a supernovae, which also overlap on the upper end of Cepheid variable stars. These are stellar explosions that happen at the end of a very massive star's life that always have the same brightness. And so we can get their distance based on how bright they look versus how bright we know they are based on the physics of how they explode. And because they overlap with Cepheid variable stars, we can calibrate their distance with the known distances from Cepheid variables, which we then calibrated based on parallax. And we can get their distances out to, so this is 1,000 megaparsecs, so that's 320, that's several hundred million light years right there. And then you mentioned quasars, quasi-stellar objects. Those are radio objects. They're probably accretion disks around black holes, up to more than 10 billion. The speed of light travel time has been over 10 billion years. So we're not going to get a speed of light travel time older than the age of the universe. But once you get out to these distances, the universe has expanded so far that it's not 10 billion light years away. It's actually much further because of the expansion rate of the universe. And so the speed of light travel time has been 10 billion years. But since that light left, this thing has moved away further, and the lights continue to get to us. So let's see.
Kirby?
Yeah.
Question. So does that mean then that the visible universe is becoming more visible over time?
Yes, it does. Yes. So imagine a sphere centered around the Earth that's just based on the speed of light travel time, and it's literally 13.8 billion light years in every direction. And as the universe ages, there's more time for light to get in, and so this sphere around Earth gets bigger and bigger. And no matter where you were in the universe, that sphere would continue to get bigger around your observation point, as there's more time for light from even further away to come in. Now, just a minute, Andrew. So the linchpin for Big Bang cosmology, that the Big Bang really did happen, that the universe started in this almost infinitesimally hot, infinitesimally small point, 13.8 billion years ago, comes from looking at the sky with microwaves. This was first detected, I think, in the 60s, and we've had a series of spacecraft, more sophisticated ever since, that have been looking at this in greater and greater detail and sensitivity. One of the more recent ones is the Wilkinson Microwave Anisotropy Probe. Anisotropy just means things are different in different directions. And it's looking at the distribution of microwave. This is like if you looked at the sky with microwaves With your microwave vision, you would see this. This is the spacecraft in the clean room prior to launch. This was predicted to happen, to exist, before it was detected, if the Big Bang was true. So this is a case of empirical evidence leading to a testable hypothesis that was then confirmed, strengthening the support for Big Bang cosmology. That's mainly what yeah, Brad.
Inconsequential question. If the observable universe continue to expand, is there the possibility that we will start seeing starlight from stars that have them beyond the edge of the observable universe? Is there the possibility we'll actually be able to see more stars in the sky with the naked eye?
No.
Okay.
They're too dim.
But if there was a huge mirror out there, you could see the creation of the Earth. And I guess it would have to.
Just coming back, Andrew.
So if you're saying that the universe is, the universe is expanding, you're saying that as the universe expands, we'll be able to see more stars?
Yeah, Brad, I just want you to see a supernova going off in a galaxy.
Oh, look at that.
This is putting off as much light as 100 billion stars for a brief fraction of time. That's a star exploding, creating the elements that make up our bodies and tables and churches and
Chairs.
yeah. So now, go in peace.
Part two.
You don't want to be too close to one of those.
Part two of my question. So if we're ever expanding and stars are getting farther away from us, how are we able to see more light if they're ever expanding and getting farther away from us?
Because
It's had time to get to us.
because there's more time for the light from them to get to us.
Okay, so the expansion of the universe still doesn't overtake the speed of light. Correct.
Not yet.
Not yet.
So the universe is most likely speeding up in its expansion. At some point, the universe will start. So the universe is the only thing that's allowed to move faster than the speed of light, according to general relativity. Space-time can expand faster than light, but nothing moving within space-time can, according to general relativity.
Within space.
So me moving around, I'm not allowed to move faster than light. But the dimensions that I'm moving in, those are expanding. Those have been expanding ever since. Those are allowed to expand faster than light. And galaxies are riding on the wave of space-time. And so eventually, we predict when the universe is 100 billion years old, this is a trillion. Of course, we can't test this, so this is speculation. With the universe expanding faster than light speed, your Hubble horizon will start to shrink to the point where the only thing we'd be able to see is our own galaxy, which would be sad.
Because it's too dim to see things beyond that.
No, because it's literally, it's not too dim. It's literally the light can't get here from there.
Right, because it's going up. It's going out too
Yeah.
fast.
Light can't keep up with how fast the universe would be expanding.
Wow.
So then, in theory, the universe could be way bigger than it really is. We just can't observe it.
The real universe is larger than the observable universe.
Right.
Most likely, yes. That's where
Or
the
the gravity of all the suns will start bringing the universe in.
That probably not actually, surprisingly. We're getting close to quitting
there are
time.
two possibilities. I read somewhere that they don't know whether they'll continue to expand out where we can't see anything, or everything will start to eventually come in together and everything will just
Crunch.
become one big mess.
You're right, we don't know, but the direction of research is pointing to the universe expanding in its acceleration that overwhelms gravity to pull things together.
Okay.
So one of the boring things, I have to say, one of the boring things about young Earth creationism is that there's no time for anything cool to happen in the universe. Like, this is a computer simulation matched to real observations of galaxies, where the galaxies are colliding and interacting gravitationally. And we see these snapshots, because these things take hundreds of millions of years to happen, we look out in the universe and we see galaxies that are interacting. And if the universe is only 6,000 years old, there's no time for that cool stuff to happen. That's boring. So we can't see any one galaxy go through this whole gravitational dance, but we can look out at lots of galaxies and see them at different stages of this. It's just like taking a photograph in a forest. You see some young trees, some middle-aged trees, some dead trees laying horizontally. And because it's only a snapshot, you can't see any, you can't prove this tree grew up, it got really big, and it fell over in a thunderstorm. But you can infer that because you're seeing different ages of the lifetime of trees represented in lots of trees. Same thing with looking out into the universe of galaxies.
So Kirby, does that account for the different shapes of galaxies that are observed? Just this gravitational interaction between them?
It partly does, yeah. We think that galaxies probably start off as small spirals, and then over time they actually form, so like spirals like this beautiful portion of a spiral galaxy here. The core is here, and there's a beautiful spiral arm here. Oh, yeah, actually, Drew, you can hit that light because the kids are gone. Other light? Oh,
You have.
there we go.
Yeah.
Like, these are just beautiful. This is M83. There's another barred spiral galaxy. Our Milky Way galaxy, we're embedded inside, so it's hard to see what we look like. But we probably look like this, except with another 2 arms going out through here. So we think we're a 4-arm barred with this bar going through your spiral galaxy. 100,000 light years from end to end. 10,000 light years thick. This is our galaxy taken from somewhere on Earth. Time-lapse photograph. Here's literally the center of the Milky Way galaxy in the direction of the constellation Sagittarius. You can see this bulge in the center of our disk.
Can I go there?
Please, I'd love to. Let's see. This is a foreground star. So this is not a star in this distant galaxy. This is a foreground star. So we think the large-scale structure of the universe is basically like a sponge, where all the galaxies are basically on the surface of the sponge, and then there's huge voids in between. And this is based on lots and lots of mapping of the universe at different wavelengths of light in lots of different directions and different distances. And so the evolution of the universe would go from fairly compact to over more and more time getting more dispersed and looking more and more filamentary in nature. And I just want to conclude with some scripture passages. All of this, we do science to the glory of God. We figure out Earth's age to the glory of God. For you make me glad by your deeds, Lord. I sing for joy at what your hands have done. How great are your works, Lord. How profound your thoughts. Psalm 92. Job 38. Can you bind the chains of the Pleiades? This is interesting that these constellations existed way back then. Can you loosen Orion's belt? Can you bring forth the constellations in their seasons or lead the bear, Ursa Major, with its cubs? Do you know the laws of the heavens? Can you set up God's dominion over the earth? Psalm 111. Praise the Lord. I will extol the Lord with all my heart in the council of the upright and in the assembly. Great are the works of the Lord, barred spiral galaxies. They are pondered by all who delight in them. Glorious and majestic are his deeds, and his righteousness endures forever. Job 12, this is an injunction to do different types of science. May the glory of the Lord endure forever. May the Lord rejoice in his works. He who looks at the earth and it trembles, who touches the mountains and they smoke. Psalm 104, he set the earth on its foundations. It can never be moved. People used to look and see science in this, saying that the earth was immovable and didn't orbit the sun. This is just being poetic. It's not saying earth is literally immovable. You set the earth on its foundation. It can never be moved. You covered it with watery depths as with a garment. The waters stood above the mountains, but at your rebuke they fled, etc. But I just wanted to end this bit on geophysics and astrophysics to the glory of God. And I want to respect your time because the service is starting soon. But next week we'll talk about the evidence for biological evolution. So, thank you.
Yeah, thank you.